welcome to episode 63 of the Meta Tech Podcast, an interview podcast by Meta where we talk to engineers who work on different technologies. My name is Pascal, and I've once again fallen victim to Pascal's law of podcasting, which states that pre-announcing a topic over a month in advance will drastically diminish the chances of it actually getting recorded. I'm sadly approximately 400 years late to make this just Pascal's law, which was claimed by Blaise Pascal for the principle of transmission of fluid pressure in 1653. But I'm here, of course, referring to the fact that I ended last episode with saying that we will likely be talking about mixed reality, which inevitably caused scheduling chaos, making this an impossibility. But that doesn't mean that we won't have a great topic and a fantastic guest, because this month I will be talking about Rust with our guest Aida. Rust is a first-class language here at Meta, and now often the choice for new projects that would have traditionally been written in C++. And yet there are still millions of lines of well-authored and battle-tested C++ out there that won't be rewritten anytime soon. This is where CXX comes in, which enables seamless, well, more or less seamless, we will get to that a bit later in the interview, interoperability between Rust and C++. I'll be talking to Aida, who worked on one of the very first teams here at Meta to use Rust, to discuss her experience of interfacing with C++, how async Rust throws an additional spanner in the works, and how she managed to eventually overcome all those issues. This is a fairly meta-light interview because all of these little tips and tricks, as well as the underlying open source library CXX, can be used in pretty much every project that ticks these boxes. Aida also recently gave a talk on the very same topic at Rust Nation, so if you want to see some code samples, then do check out the link in the show notes. But now, enough of me monologuing, here is my interview with Aida. We have had a lot of fairly high-level product discussions on the podcast lately, and as much as I've enjoyed those, every now and then I like to go really low-level, and I have a fantastic guest to do that with today. Aida, welcome to the Meta Tech Podcast.
Hi. Nice to see and hear you.
Well, only hearing for most of our audience, but appreciate it. Now, before we go all the way down to the FFI boundary between C++ and Rust, tell us a bit about yourself. How long have you been at Meta and what did you do before?
Yeah, so I joined Meta in 2018 when it was still Facebook. So I've been here for slightly more than 6 years. Before Facebook, I worked at Yandex as a C++ engineer. And yeah, so that was my journey.
Fantastic. So what was your first exposure to Rust then when you worked as a C++ engineer before? Was that here at Meta?
I know. So basically, yeah. So when my first exposure to Rust was within Meta when I worked in Source Control team, basically because the amount of source code we own as a company is tremendous, and no open source solution actually works for us. Around like 10 years ago, we forked from the open source material and started building our own source control. Basically everything from the server to the virtual file system to the client side. That's something that we open source, so you could check it out. It's called Sapling. But anyway, so around, I guess, 5-6 years ago, there's a decision made to start the new source control server, state-of-the-art server. And it was going to be the brand new project. And the language to write this project was chosen to be Rust. And when I came to Meta, I joined Source Control team straight ahead. And after like a year and a half within the team, I started working on the server side. And that was my very first exposure to Rust, because I've heard about the language, but I've never actually used it. It was a very interesting experience because at the time, there's not yet async await syntaxes in Rust. There's lots of like old school features. And it was very, I guess, challenging to onboard at the same time onto the new project, onto the server side, the source control, and to learn kind of like new concept within the Rust programming language.
Yeah.
But it was wonderful time, I would say.
Yeah, challenging is putting it mildly. Just the inherent complexity of a mercurial server, I think, is sky high, and then learning a completely new programming language as part of the onboarding process as well. That sounds like a lot.
Yeah, I mean, I feel like it was a lot because my first project was to we were working on the API service around our source control server, basically the service that provides API for other infra projects like test infra, build infra, stuff like that. And I was working on the thing that will basically in some algorithm to fetch the history of changes for different files and stuff. And it was a fun algorithmic project, but just like the fact that I had to kind of learn new concepts, work in a very high multi-threaded and heavy async code environment, that was challenging because I haven't done that frequently in my life before that.
Yeah.
And I remember a couple of people in the team were helping me to onboard on that. And I think I spent a couple of hours with one of the teammates, and he talked, like basically trying to explain me the concept of multi-threaded programming in Rust. He almost gave me a lecture on functional programming. It was helpful, but also it was very interesting.
Yeah, I can imagine. And if you're coming out like, what the hell is a monad out of the discussion where you want to learn about?
And he started
really?
just from that. Yes.
Oh my God, I'm just making something up here. But
no, that was literally like first 15 minutes. And I'm like, okay, how does it helping me to write code though?
That's hilarious. I would like to have that person on the podcast at some point and talk about monadic multi-threaded programming. So maybe you can make that introduction. But that is super cool. And also this gives me an opportunity to say thank you to you. We've had an episode about sapling before, but this is honestly one of my favorite projects within the company because as an engineer working on our code base, as one does as a software engineer, I use this every day. And I think I joined roughly 1.5, 2 years before you. Mm-hmm. And the internal code name of the project before and after is absolutely night and day. Things have become so much faster working with Mercurial these days as they were before. And well, that is a no small parts to your work on the backend server.
Oh yeah, you're not alone here because I honestly think that source control is amazing in the company. Like I've been working in other different companies before, and I could say that source control here works really well, and it's really fast and came a very long way. Like from the moment I joined, even as an experience. So basically, folks within the source control team try out things earlier than everyone else. Basically, we're in alpha stage of rollout, and it was a nightmare first couple of years. Source control is also on-call was also a bit of a nightmare, but
I can imagine
it came a very long way. Yeah,
you're in the critical path of absolutely everything there.
Yes.
Yeah, and I think there are also so many interesting cultural consequences of having fast source control. I worked at a company before that had a small scale monorepo using Git, but without any optimizations for it. And because everything was so slow, you really think hard about when you want to interact with it. So the question of like, when do I pull? When do I rebase? When do I even commit? These are really things where you kind of schedule your day around. And now that I have fast source control, I can just commit left and right and rebase this on top of that. And I can be so much more agile. I can make smaller commits, ones that are more atomic and actually encapsulate things the way I want to do it and not how source control makes me do it.
Yeah, that's actually really cool that you mentioned that, because I think the concept of like having a smaller commits and working on the fresh copy of the repo is very nice and productive. I mean, it makes your work way more productive than before, because having so many engineers working at the same time on the same repo is just, it's a bit of a nightmare in terms of like how much concurrency issues with committing stuff and conflicts you can run into, right? Yeah. And the idea that the reads are so fast that you don't really think about that you can just pull every like couple of minutes and it will be still fine and it's not going to disrupt your workflow. That's really cool. I really appreciate that.
And when I see somebody post a large code review and I ask them to maybe break it down along these kind of fault lines that are there, I'm not asking them to spend the next 3 hours painfully waiting for the Mercurial to actually finish their work. But no, this is quite feasible to do within like 5 minutes, because we have a beautiful HG split command that helps you and rebasing is fast and all of this. And well, I think I could talk for the entire hour that we have about source control with you, because that to me is a fascinating topic. We're actually here to talk more about Rust and C++, so maybe I'll just try and steer us back in that direction. Can you, maybe just from your perspective, because you obviously don't work on a Rust Foundation team, share your view of how Rust is used today at Meta?
So basically, when we started the Source Control server on Rust, it was a very big decision to introduce Rust to the company and to such a, I guess, core and important infra project. Fortunately, we had a very, very smart and very cool people who were in the Rust community, and they pushed at the time towards using Rust. It was a risky decision, I would say, because basically there's no precedence within the company, but I think it proved to be one of the best solutions we made, because since the time, Rust became one of the formally recognized system programming language within the company, and many new projects that are being developed in Rust, in like comparison to, for example, or instead of C++ or Python. Like, for example, it's a bit weird, but like good example of that is lots of like CLI tools. Before they would be written in Python, now they are written in Rust, because the load time is actually so much faster and smaller than for Python CLI tools.
Yeah, I actually did this once for a project that I worked on. We took over a different tool that was there for emulator management. And it was a simple CLI tool to just kind of test how to interact with a Thrift service. It wasn't really used in production. It was just for engineering purposes. But it really bothered me that it took 30 seconds. And based on the logs, I could see that was just for initialization. So I thought, how about I just spend like 2 hours try to rewrite this in Rust? And that brought down the startup time from above 30 seconds to, I think, like 0.5 seconds. And I was so happy. I didn't care that there were only like 3 people actively using it. I could test my changes now without, my mind wandering what else is going on in my diff inbox or whatever, but could stay focused on my terminal. And I think that experience is fairly common. There have been lots of internal tools, as you've mentioned, that people have just tried to rewrite in Rust and see what happens. And usually the outcome is it's orders of magnitudes faster.
Yeah. And with like some libraries like Club coming a very long way from like what it was in previous versions, it's so much easier now to write CLI tools with all the syntactic sugar. It's really easy.
Yeah, for people who don't know, Clap is a library for building CLI tools and specifically passing arguments, and it provides really nice automatic help messages and all that. But yeah, so you mentioned that new projects might choose Rust now. We have really nice integrations with Buck and all the CI tools, whatever you want to use there. So it's really first-class citizen these days. But obviously, there's still a lot of code out there that is written in other languages, for instance, C++. And I guess that's what we want to talk about. I mean, I could ask you, like, why don't we just rewrite everything in Rust? I think the answer is pretty straightforward. There's just a lot out there, and that would take time that we probably could spend better on actually building new stuff. But if people want to interact with C++ from Rust, what were the options before and what have we been using recently?
Yeah, that's a very good question. So my journey with the FFI layer between Rust and C++ started, I would say, 3-4 years ago when I was still working on the Source Control server. And because, again, it was one of the first projects ever written in Rust in the company, and the biggest one, I think the first biggest one, there is no integrations with many other supporting tools. Like, for example, Source Control uses storage, and in order to talk to MySQL, for example, you'd have to have a client. But we didn't really have a client for Rust. And the very first way of like communicating to the database was a very hacky sidecar way of talking to some kind of proxy process running separately in the machine, and that process would talk to MySQL. So it was, I would say, iteration 0 of talking to a something. Then when basically people recognize that we do need to have internal libraries for Rust in order to use tools, we started introducing bindings. I think one of the first projects for that was for which we actually worked on the bindings was MySQL client. Again, as you mentioned, it's not feasible not most of the time, but I would say like fairly large percentage of times to not rewrite things from C++ to anything else. And MySQL was one of that. So we decided to basically create a wrapper library on top of the C++ MySQL client. And for this reason, we used bindgen because that was like the mainstream way of making Rust and C++ talk. Yeah, then later we switched to CXX library that was written by David Tolney, and that solved a lot of potential problems with memory leaks and segmentation faults, stuff like that.
Right. So I think I used bindgen as one of my first Rust projects, or like I should say modern Rust, because I used Rust fairly early on, where it had very different syntactic elements and a garbage collector built in, so really unrecognizable from what Rust is today. But the first thing that I wanted to pick up was build a wrapper around Yoga, which is an open source Flexbox library that was published by Meta. And my God, it was really hard. I didn't understand Rust really well. I didn't understand C or C++ very well that it was written in. It was a disaster. Mm-hmm. And I think bindgen didn't really help because it's a great library. I don't want to diminish the achievement there, but it still leaves a lot of the thinking on the actual author of how to interact with it. So that's kind of my view. But can you talk a bit about the kind of shortcomings that bindgen might have and that you have discovered building this kind of wrapper around MySQL?
Yeah, so you're right in terms of like there is a lot of responsibility on you as an engineer to figure out what to do, and part of that is that it's in a way like low level, but also like a high level library. So it's a low level because it basically generates very like unsafe external code, and that's pretty much it. But it's a high level because you basically can feed it a whole library, C++ libraries for it to generate bindings for Rust. And that can be a benefit, but also it hides a lot of errors that you can run into basically in production or in runtime, because it's just best effort binding generation. It just basically generates something that may work, but also may not work.
That's exactly my experience with it too. You get so used to this model of writing Rust, and if it compiles, it actually works.
Yes.
And that was completely inverted. I got it to compile, I was so happy, and then boom, a seg fault.
Yes, yeah. Honestly, the only time I got seg faults in Rust was when I was trying to build it with C++.
You and me both, yeah.
Yes.
Cool. So how does CXX improve on that experience? I know it's a completely different model, but can you contrast the two a little?
Yeah, from my personal experience, I feel like CXX tries to basically, I feel like you control things way more in CXX rather than with bindgen, but at the same time, it provides you high-level abstractions that can eliminate parts of the problems that come from bindgen. Like, for example, you're responsible as an engineer to specify whatever functions, methods, and classes you want to expose. So it's not going to automatically generate it for you. Mm-hmm. So you have to actually write this external code. However, you have access to smart pointers that are seamlessly translated from C++ to Rust. Yeah. And that is a huge difference between bindgen and CXX, because the amount of time you have to deal with pointers and like moving objects back and forth between C++ runtime and Rust runtimes, it can be quite a lot if you're doing async code. And that helps to eliminate most of the seg faults and memory leaks.
Right. So you mentioned that when you started on your source control project, that async Rust wasn't a thing, but now it is, and I'm sure it is. Well, I'm sure I've seen it. It is a thing. We use it very extensively. So how does that fit into a C++ interop story? Because as far as I understand, there's like Rust async has a fairly specific meaning on what a future in this context actually means, but it's not really defined in C++, is it? So how do the two worlds interact?
That's an interesting question, because they're kind of like, the concept is quite similar, but first they're different. Second, they don't really know anything about each other. Yeah, and that's, I think, the biggest problem. So, for example, in C++, when you basically do a future, it's like a promise. So basically, it will be fulfilled. This value is going to be available at some point of time, and the execution is kind of started. So basically, you already kicked up the process to execute this task, but it's just not available just yet. So when you do async code in Rust, when you just create an async function, it's actually not yet promised to do anything just yet. It's just a function like a lambda or something. It's just a defined task. Yep. It's not being executed yet unless you specifically poke at it and like, okay, start execution, please. Right. And that's just one difference between these two. But when we're talking about the FFIs between two languages, I think it's nice to imagine it yourself as two kind of separate, concurrently running runtimes from C++ and Rust that do not really know anything about each other. It's like two processes that run in parallel, and like unless you actually make them communicate through some inter-process communication routes, they're not gonna. And that's the problem that you have to deal with doing FFIs.
Yeah, so this is a genuine question because I don't really know how this works in C++, but is there a standard for async futures, promises, whatever, or is it more like based on whatever library you pull in? I know we use Folly a lot internally as our kind of C++ standard library that defines its own future type, I believe. So is that defined, or is everybody just kind of making up on the fly what async means to them?
Oh, that's a good question, because I don't think I can talk in depth about that because I'm just not that experienced with modern async C++. But I believe that it's in general, it's quite library agnostic, I think. So there are some kind of defined interfaces within the standard library, but basically it depends a lot on the library you're going to use. At Meta, we do use Folly a lot. So yeah, that's basically what I have most experience with. However, I believe that you can get another like options for the few async programming, yeah.
And the way you've defined it already, it's about just kind of making sure that the semantics of how you use it kind of translate to the other side so that you don't have a future that comes over on the Rust side that already does work before you pull on it, for instance, right?
Yeah, I feel like the whole concept of like async FFI between two languages, it's more of a question of understanding what's going on rather than like using a particular libraries. Yeah. Because like either with BindGen or CXX or whatever other tool you're going to use, I think the best way to approach it is to eliminate the magic out of this equation. Basically, not rely on the tool to basically figure out everything for you, but actually understand what's going on. Because if you, not 100%, but when you rely 100% on some particular tool, you may run into issues in real time.
Yeah, and you've said that unlike BindGen, you actually still need to write your interfaces, and you can kind of define what this boundary should look like. So how would you do this if you have a C++ future and you want to use it in Rust with a kind of standard await syntax, for instance?
Yeah, so two things. First, when you want to expose something to Rust side, in general, it may be a good idea to create a more simplified API for the Rust. Yes, CXX can, and I think that BindGen as well, can generate you bindings for the classes and stuff. But sometimes it can be just easier to create a couple of kind of like thin API layer on top of whatever you want to use in either side to make it just easier to translate things. Yeah. On the other hand, the second thing, when you try to run, for example, C++ future from Rust, you have to understand how the runtimes work and how the futures is going to be executing. The goal on the Rust side for us is to make it asynchronous, because if we would like to make it just synchronous, we could, block and wait on the execution, and that's it. We don't really want to do that because that's the whole reason. Otherwise, we could just create a synchronous version of the function on the C++ side and just, FFI it to Rust. So I think the basic idea within the async concept is to think about these futures as a processes or like the things that do not know each other but want to communicate. And for this reason, you can use a channel for them to basically exchange messages and let each other know when the execution is complete, basically. So the basic idea for the running async C++ code will be to create a FFI synchronous version of the function, basically, which gonna call the async function in C++. And as I mentioned before, the future in C++ already starts the execution. Mm-hmm. So whenever you call this method, it's gonna call this task, basically, it's gonna start the execution. However, now in Rust side, we have to understand when that's complete, basically, when the task is complete, and understand it asynchronously. So there is a great thing called one-shot channel, asynchronous one-shot channel.
I've used them. Yeah. Yes. Actually, I like the channels in Rust a lot. They simplify so much otherwise really tricky cross-thread magic away. But sorry, continue. You use it.
No. Yeah, you're completely right. And the magic of one-shot channel is actually that you can write to it synchronously, but you read from it asynchronously. So basically, on the C++ side, the only thing you have to do is basically write message to the channel when the future is ready, and let the Rust side know that, hey, this is the result, you can take it. And on Rust side, you just have to await on the channel to receive a message. So it actually becomes quite native to Rust, so you don't have to create like weird constructions or anything like that. And the beauty of FFI, it can be a two-way bridge. So basically, in order to make C++ send you a message to Rust, you can just create a small function FFI from Rust to C++, and C++ can just call this function, and that's it.
Right. So in fact, CXX still makes you do a few extra steps to make this work, because in the end, you still need to write a bit of C++, but you have access to Rust core primitives like the channels. Well, I'm not sure if in that case it's actually a Rust primitive or it's from Crossbeam or some other crate. But the fact is you can just expose Rust to C++, get it back, and write fairly standard code on both sides to interact with it. And I guess the beauty is really that CXX generates in both directions and not just like bytegen from C++ into Rust, right?
Yes, I think there is a C bytegen, and
okay.
Yeah, so I think it's possible to do that with bytegen as well. So because the first iteration of the library we did from Async was actually on bytegen, and it worked the same way. So basically, you still have to get the channel, and it's just a lot of raw pointers that you want to avoid. And here's when CXX comes and solves this problem.
Yeah, so point is actually a good topic. I wanted to ask you about this because you're still making a lot of assumptions about things kind of going right on both sides. You mentioned you have some runtimes on both sides, for instance, and on Rust, as I understand it, you are not forced to use any specific async runtime like Tokyo with CXX, right? Because you're writing the code. Is that correct?
Yeah.
Okay. But so like one runtime could just disappear for whatever reason, or you have a timeout and that's not properly communicated. And now, oops, you have a memory leak somewhere because like one side is potentially waiting on another thing to deallocate it and doesn't actually know about it. So how do you handle all these cases where things don't go quite as planned in the synchronization between both sides?
Yeah, that's a good point. So basically, I can from the top of my mind, I can think about two main problems that can arise from this kind of two separate runtimes. So first problem is what you mentioned, the memory leaks. Basically, when a chunk of memory just being lost in between things because no one owns it anymore and no one took care of it and freed the memory. And another thing is potentially, I can't say whether it's worse or better, but basically it's a segfault when a thing does not exist anymore, but the runtime is not aware of it. And when we do a lot of FFIs, you have to make sure that the object are owned by things they have to be owned by. That's a bit weird saying, but basically, when we're thinking about the asynchronous code and, for example, the channel that I mentioned before, so how does C++ writes a message to, basically, how does C++ do any work? You call the function, you pass some kind of arguments to this function, and it performs some actions on the arguments, right? So assuming you have an object that is currently owned by Rust because it was exposed from C++ to Rust. And now Rust has an ownership of this project, or of this object. So you want to call an async function on C++. You call a function, you pass the pointer to this object. Now, what if Rust runtime shuts down? It can happen if something that was running concurrently to this particular task panics, like something went wrong, it shuts down. So C++ runtime is still executing, and it's actually started the execution of this task that operates on the object. But the object does not exist anymore because the Rust side owned basically owned this memory. It owned this object, and when the stack was unwinding, it basically freed all the memory. And here you have Sigfold.
Right.
Another thing is like when you have a thing stuck in a channel, for example, that's like no one cares about. So basically Rust shut down, and it doesn't read from the channel. C++ for example, let's step back. So basically, if Rust starts to call C++ and it sends an object through the channel back to Rust, but Rust decided to not read anything or just like whatever. So yeah, here's you have like
we all have those days,
yeah. So lots of things like that.
Yeah. So I guess there's no kind of one size fits all solution for this kind of set of problems, but what's your general approach towards fixing memory leak issues, for instance, that result from behavior like this?
Well, smart pointers. Not really though. There are things that in general is very nice about Rust and like about, I guess, modern C++. Smart pointers, and the idea of that the memory is always accounted for. So you always know who owns what and how. And that's something you have to bring to the FFIs as well. When you're using bindgen, you have to clearly understand who owns what and make sure that in case something goes, basically you have to think about the worst case scenario and make sure that things are being like freed and took care of. So one of the examples of that, for example, when you expose objects from C++ to Rust, you may not think about the destructor. You may think about that if destructor is already implemented on C++ side, I don't have to do that on Rust side. Well, it's not true. The Rust doesn't know anything about your destructors, and you have to specifically expose them and call them from Rust. It's actually quite intuitive when you think about that, because from the Rust perspective, the object is just arbitrary chunk of memory. It doesn't know the size, it doesn't know the layout. It's like it knows that it's something, but I mean, there are simple structures like enums and stuff like that that can be translated seamlessly. Or like, for example, something that CXX, for example, has is the seamless translation between the vectors and the strings, which is quite cool because that's something that will run the destructors and like everything for you. But for more complex objects, you have to think about things like that. So first, I would say think about the lifetime of the objects and how you would free the memory and who's going to own them. And second, use smart pointers. If you can't use smart pointers, use the reference counters, anything possible to make sure that the object's lifetime is bound to the runtime that can basically terminate first.
Right.
Or the last.
Yeah, totally. So I think it just forces you to actually think a lot about your object and what it means. In this case, we're talking about the lifetime. Another question I have is, what about attributes from Rust like send and sync? So whether you can send objects between threads or might even share things between threads. You just mentioned an example of you have some sort of undefined shared ownership and then one just frees the memory and things blow up. What about thread safety? How do you think about that?
Yeah, that's a good point. So basically, just to, I guess, for the context, basically send and sync traits are one of the like basic traits for sync programming in Rust that allow to specify to the compiler that the object we're talking about can be sync safe or thread safe. Or sync safe meaning that it can be shared between threads, and send safe meaning that it can be sent from one thread to another. Why it can be useful for, like, for example, send trait means that if you want to spawn a task on different thread, you can do that. Because if the object is not send safe, you can't do that. The sync trait can be useful when you want to access the same object from different threads by definition. But yeah, when we're talking about the custom classes and objects in both Rust and C++, so for Rust doesn't really basically define send and sync traits for the custom complex objects. So you have to think yourself whether it's send or sync safe. And it's more complicated for C++ object because you have to decide whether this is send or sync safe.
Yeah.
And you may not be able to decide to make a decision yourself without understanding how C++ works. So basically, if you have...
That would be me.
I'm pretty sure you'll be fine. So when you see some random library object and you haven't seen the implementation, you just see that, I don't know, that the definition and the name, and you want to expose it. You can't just say that it's send and sync safe because you don't really know. And for example, thinking about the MySQL, right? Imagine you have a MySQL client object and then you have a connection object. So if you want to, basically use MySQL client object to get a new connection, and it's intuitively sound to have MySQL client to be sync safe because it's basically can be shared between different things, because the only thing is basically read thing. So you get something from the client and you don't really change the state of the object. Well, I mean, you probably do change that, but I guess like the design of this client is to be shareable, while the connection is a uniquely owned object. Mm-hmm. Usually, the different implementation can be different, but for example, we imagine that connection is a uniquely owned object. So if you don't know that, you may mistakenly say that it's sync, and you run out in a lot of concurrency issues on Rust side.
Oof, that sounds like a nightmare to debug. Yeah.
Yeah. So I would say it involves a lot of C++ code reading to figure out things like that.
Yeah, you would wish that C++ had their own kind of set of annotations to actually make those guarantees that you could copy over.
Yeah, that's a good point. Yeah.
That'd be nice.
You can suggest that to C++ Foundation.
Oh, right? I think I'm good. I've got a lot on my plate. But yeah, if anybody else listening to this wants to pick this up, you can take my idea and run with it. So yeah, that is super interesting. And I guess like one additional problem is that whenever you have an upgrade of a library, something that used to be send and sync might no longer be because of some changes to the object structure. So
yeah, but unfortunately you can't programmatically avoid things like that.
Yeah, of course.
Yeah, the only thing you can do, I guess, is put a comment.
Yeah, for sure. I'm just thinking about, even when writing Rust, this can sometimes be a problem where you say, hey, this object is send and sync, and now you've locked yourself into this basically forever. Otherwise, you'll break forwards compatibility, or actually more like you'll break backwards compatibility if you make that change in a really major way, because people might build their entire code around it. And I guess the same is true now, where you have to revisit every single one of these kind of attestations that you've made about thread safety for each object.
Oh, I have a very good anecdote about the sentencing. Basically, yeah, because these are unsafe traits. You have to, when you're implementing them, you have to do unsafe implement the sentencing for the object. And I remember seeing a screenshot of a code somewhere. So basically, a person who wrote the code, they were not basically aware of how unsafe works, and they thought that using an unsafe word means you're telling the compiler, do not do that. So basically, when they did unsafe implement send and sync, they thought they're saying that, hey, this is not safe, do not do that. But what compiler thought, it's like, trust me, bro.
Yeah, I don't want to laugh about it, because that feels like a very easy mistake to make when you need to Rust. And especially at this company, you don't have to have some sort of certificate that you're an expert in the language to make any changes. I go around all the time and make changes to code base that I have no idea how they work, and I just kind of rely on other people reviewing it, or CI catching potential bugs that I might introduce by doing it.
Yes.
Right. Okay, Ida, we are almost out of time, but I want to just briefly take a quick step back because you've told us so much about C++. Async Rust in general, I've mostly tried to avoid it, quite frankly, because I feel like there's even an understanding within the kind of Rust community that if you can stay within sync Rust, stay within sync Rust. It is much easier to work with. So I just wanted to kind of ask you, if you could wave a magic wand and improve like one specific aspect of async Rust in terms of its ergonomics, or really anything, it could even be with C++ again, like what would that change be?
Oh, that's a very hard question. So, I mean, first of all, I think I know why people want to avoid async. Except for it being quite complicated and blah, blah, blah. The thing about async comparing to sync Rust is that this idea of like when it compiles, it works, it's not applicable for async. And that's a huge problem. Like it's a huge problem, first of all. Second of all, I feel for me personally, async can be tricky because it has a lot of magic, and I don't like magic in programming. I want to know why it works, and don't just rely on the thing that it works for now and may break later. And I think a lot of issues that I see myself in async came from sub-executor problems. Because if you do a very heavy async code, as we did, for example, in social control, that can cause a lot of problems with future starvation, with long poll times, with lots of things that you may not think ahead of time, just because you're not aware of the issues like that. Like one of the issues, it's quite related to the FFIs that I worked on. Basically, the second stage of my project was to integrate the Rust MySQL library into our project, and turned out that it didn't work straight ahead when we used the connection pools. And the reason was that we just had so many threads and so many concurrent connections that it couldn't cope with it. So we basically had to make a multi-threaded connection pool. So basically lots of concurrently running connection pools. And that's something that you don't really know ahead of time, I guess. Yeah. I mean, now I know, but at the time you're kind of like, oh, whatever. So the thing that always helped me a lot is having a good tracing mechanisms around futures in async code. So I would really love, I guess, to have some kind of out-of-the-box solution for that, because at Meta we have our own kind of custom libraries that we wrap futures around, and basically they will log stuff about poll times and execution times, and we can debug later. So I think something like that would be wonderful.
This whole problem of spawning too many futures, that is just way outside of my comfort zone and experience. So this is actually a really interesting thing that I wasn't aware of. That's a really good way to wave your magic wand. And now we're sadly out of time, Ida, even though I could continue, especially on the source control discussion with you for ages. So thank you so much for making things here at Meta faster and making sure that we have safe communication between Rust and C++ in both directions. Thank you so much.
Thank you so much for having me here. Thank you.
And that was my interview with Ida. I've been pretty open about the fact that I'm quite the noob when it comes to both C++ and Rust. So I hope I didn't offend the experts in our audience too much, but if I did, please send your hate mail to me on Threads or Instagram, where we are at MetaTechPod. This is also the place to send in questions you'd like to have answered on the show or topics you'd like to hear about. I won't mention anything about the next episode now, because we all know what this will lead to, and instead I'll simply thank you all for listening. This has been another episode of the MetaTech Podcast. Until next time, toodaloo.